Okay, our lesson today is graphing the equations ax squared plus bx plus c, or a quadratic. So it says we're going to transform quadratic equations from vertex form to standard form. We will graph them and interpret them, and we will use the quadratic equations to solve problems dealing with velocity and acceleration. Okay, now we've already started experimenting with graphing them, so we should be good with where we're at on the calculator, but let's see. As an example, when we talked about the translation, this would be just, a good little review. How would each of the following translate? So I have some square root graphs. I have some things happening inside, some things happening outside. So let's just double check with our graphs when we know what the square root graphs does. And so these would be an example of some of the harder quadratic ones to graph. So let's reset and let's choose one. So right now we're saying, all right, what's happening if I choose this first one? It's basically a square root, the parent graph, and that'll be in red. And then if we do a -4, subtract 4 outside of the square root, what will happen? So we're going to show you that the parent graph in red, there's the square root graph, and then that -4 took it 4 units down, a vertical change from where it was originally. The next one looks like the exact same setup with a +1. So you should be able to say, wait a minute, that one's going to be that same parent graph, but this time it better be going in the other direction. So we do a reset and then choose that second one. There it is. The parent is in red and the new translated. So do we see any more that have that? Probably not without a negative in, so we're good. So now let's go down to this next one, f of x equals the square root of x minus 4, where the x minus 4 is all underneath the square root. It's a little different than up here when we were looking at, hey, it's outside of the square root. So what effect will this subtract 4 have on, and think of it this way, the x value, because that's what it's attached with, that's what it's paired with, that's what it's grouped with underneath that square root. So if we reset and then choose, we will see that our original parent function again is in red, and now this was a move 4 to the right from where we were currently when we were looking at the parent graph. All right, the next difference is that negative out front we talked about before. So let's reset. And we know our parent graph is going to go out there. And with that negative out front, what happens? It reflects it over the x-axis. So on this next one, you should be saying, well, it's going to be that reflection, but it also has that +2. What were we doing when we had movements outside of the x? We were moving up and or down. So again, reset. We want a reflection, but it's going to have to move 2 from the parent graph. So it's going to reflect, so that's why you see the green arcing different way, and then it's 2 up from what the parent graph was. If we put a number out front, that caused a little different situation where we were talking about a stretch or a compression. So reset in red. Now we've got it compressed a little. And you can see how these are going to work. And obviously you would have your calculator with you to be able to check your solutions. But knowing and noticing the pattern of if it's inside with the x, if it's outside of the square root sign, if it's in front, each of those things have a different characteristic or movement to them. All right, let's move on. Let's talk about any parabola whose equation can be written in vertex form, which we've shown you already, which is that hk that helps us determine its movement, can also be written in what we call standard form, ax squared plus bx plus c. So knowing that, we want to be able to take and change equations so you can answer things like, are these two equations equivalent? Why or why not? So here's two equations. They definitely don't look alike from the beginning, but they have some characteristics the same. So the question is, if we started simplifying, and we'll just go through it. If we start simplifying, so we simplified the parenthesis first, are using our square binomial rule. X plus 1 turns into x squared plus 2x plus 1. We then distributed that 3 throughout the entire thing, and then added that negative 4 in the end, and we got 3x squared plus 6x plus 1. This is now what we would call standard form, when it was originally in something closer to vertex form. So we can compare that to our other equation, and notice that they're exactly alike when we compare them in the same form. So when you move from what we call vertex to standard form, we're really just doing our algebra. Move things over, slowly getting y by itself, getting rid of the parentheses, getting rid of the squared, and getting standard form, which we know is ax squared plus bx plus c. So vertex to standard gives us simple algebra that we're used to. Now, in doing that, you don't always have to have a full equation, as you've seen before. We've had some that are just short, one term. We still know it's a parabola. We know that a value determines whether it opens up or opens down. Those are things we've talked about. But other times we'll have the ax squared plus bx plus c. Now, we're going to talk specifically about a quadratic equation that is based on, and I like to call it the acceleration due to gravity formula. There's velocity involved, and we have two things here called gravitational constants. If you don't know them, jot them down because they will be used. The g equals 32 feet per second squared is commonly known as the US gravitational constant, versus g equals 9.8 meters per second squared is the metric. Most of the rest of the world uses this. 9.8 meters per second squared. You're going to see those in our standard form for what I call acceleration due to gravity formula. And here it is. Look at it, and maybe by itself look at it first. It says h equals negative 1/2 g t squared plus v sub 0 t plus h sub 0. We like to say that this negative 1/2 g will sort of take care of itself, because as we just described, those g's are gravitational constants. If you know the problem is a US measured problem, feet, inches, miles, all those things can be converted to feet, which is our gravitational constant of 32 feet per second squared. You would then have an equation that starts out negative 16. However, if you read in the problem and it's all about metrics, then you're doing a 9.8 for g, and that would make half of that a negative 4.9. So one of your two starting numbers will either be a negative 16 or a negative 4.9. Now, I said memorize the formula. Absolutely. V sub 0, h sub 0, think of it initial velocity, initial height, and I will have those listed here so you can write those down as well. This is the typical science math equation where you will use it in both courses. Notice h, when we start off, is the height of the object anywhere along its path. So if I have a parabola, it represents a jump shot. You saw the basketballs there. And so it goes up and comes down, whether it makes it into the basket or not, but it's coming down. Height of the object anywhere along its path. So whether it's here, 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 that's what that h value is. T is time, and usually it's time in seconds. And v sub 0 is your initial velocity, which usually will be given to you, or it won't have any velocity. H sub 0 is the initial height. G is that gravitational constant that I talked about. That will either give us a negative 16 as our first value, or will give us a negative 4.9 as our first value, depending on if it's US units or metric. Okay, so here's an example. Suppose a toy rocket is launched so that its height h in meters after t seconds is given by this equation. And you can see we've used the equation. Our constant, our g, was used, negative 1/2 times 9.8 gave us a negative 4.9. T squared plus 20t went in, and plus the 1.5. Now, I'm just going to put down our equation again so you can see. Negative 1/2 g t squared is your first term, plus v sub 0 t plus h sub 0. So you can see what's what. We really have this took the place of that negative 4.9. V sub 0 is your 20 slot. 1.5 has to be the h sub 0 slot. Now put those into context. What did those mean again? You have the little chart right there from the last slide. So question, how high is the rocket after 1 second? Well, we don't know. This is a generic equation. You would have to put a 1 in to your calculator or into your brain, paper and pencil, and calculate what that would come out to. So go ahead and do that quickly. After 1 second, you can see we've got a negative 4.9 there. 20 times 1 is 20 plus 1.5. So do the quick arithmetic. You should have gotten about a 16.6 meters. So the rocket is gaining height still after 1 second. Now the question is, how high is the rocket when launched? You're saying when launched, so what do they want me to do? Well, go back. Initial height. How high? Does that mean, is it on a ground? Is it on a base? Is it on a table before starting? Maybe it's getting shot off something, right? And then it goes up. So how high is the table? So that initial height gives you that value. So you should have been able to say that how high is the rocket when launched? You should have said 1.5 meters. How high is the rocket after 12 seconds? So again, you're going to put your 12 in, do the math like you did on the first one. I'm going to ask another question. What is the velocity? What is the initial velocity of this rocket on launch? And you should be able to tell me the initial velocity is 20 feet per second squared. So if you got your 16 or your 12 seconds calculated now, t was 12. We have an h value of negative 4.64, negative 464.1. So some people are going to say it's in the ground. It's that. No, 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 no. I mean, it comes back and it hits the ground. So it's been on the ground for quite a while. That's what you could say at this point. So it didn't take long for that rocket to go up and down. 12 seconds in this case was too much, too long. It's been on the ground for quite a while if it's already at a negative 464. So if we ask you, go into your calculator, when did it hit the ground? You should be able to tell us that by looking at your table, your values, using a trace key, all things that we're expecting you to be able to do with that acceleration due to gravity formula for this section. All right. With that, come to class with some questions and or how your calculator worked or didn't work for you in those graphs, and we'll let you know.